We will now complete our look at the second order Cauchy-Euler equations by determining what to do when we end up with complex conjugate roots of our auxiliary equation, right? So suppose we start with our auxiliary equation that looks like this, right? So that's the auxiliary equation for Cauchy-Euler, and we solve it. And what if we end up with our lovely complex conjugate pairs like that, right? Well, remember the whole idea that led us to this auxiliary equation our educated guess that power functions are the types of functions that would satisfy the Cauchy-Euler equation. So by power function, it's going to be x raised to some power. So let's go ahead and apply that principle to this and just say that now my power is going to be a complex number, right? So we have this is a real variable x, but it's being raised to a complex power. And let's just start by taking one of the pair. Let's take the alpha plus beta I. All right, so let's do that. And if we go through and so let's go ahead and now how did we? If you remember, we handled the complex case by using a really cool result, which in its own right, even outside of the context of differential equations, is super important, right? So this e to the ix is that it's equal to cosine x plus I sine of x. And you might remember that this is Euler's result. So this is what led us to the fundamental set in the third case when we have the complex conjugate roots when we were looking at the constant coefficient Holdies, right? Well, since we have complex conjugate roots here, we should probably think about using this result again. But this result requires a base, a constant base of e, right? Well, this is not a constant base e. However, we have a fix for that. We can always go to algebra, and algebra says, if you have something like this, assuming that your a is positive, right? If you have a positive base not equal to 1, then you could do this. You could do e to the ln of ab and then bring down the b using that property of logarithm. So you end up with this conversion, right? So this is the change of base. So let's first apply this to this expression. Let's change this to base e. So if I do this, then I'll end up with e, and then it will be to the ln of, where are we? Right, so it's e to the ln of the whole quantity x, and then you'll have the alpha plus beta I like that. All right. Certainly looks like we're making it messier, but what we are allowed to do now is to take that alpha plus beta I and put it as a multiple, a coefficient of the ln, right? So then it looks like e to the quantity alpha plus beta I, and then I'm left with the natural log of x there, right? And remember, everything here is valid because of our existence and uniqueness theorem. The interval of existence, we're working with the interval where x is greater than 0. So again, everything here is valid, right? So what else can we do? Well, and we probably could have done this earlier, but we can split this into two exponentials, right? So let's say, and let me not skip the algebraic steps. Let's say I distribute the ln, so it looks like this. And then I'll have plus beta ln of xi, like that, right? And then use a property of exponents that allows me to factor this e as e to the alpha ln of x times e to the beta ln of xi. Now, this part here, since it doesn't have the I, we really don't need to keep it in this form, right? In fact, if you notice, this form is essentially this form right here, where my b is the alpha, and then my a is now the variable x. So I can just go back and I can write this as x to the alpha. That's fine. But then this one now is where I will use, and let me scroll up again so we can see it. This is the one here where we're going to use Euler's. The difference is now, instead of just having an I times an x in the exponent here, I have I times all of this. So all of this essentially replaces the x in the basic Euler's result, right? So it looks like this. So using Euler's, this I now have the quantity of cosine of beta times the natural log of x plus I times the sine of beta natural log of x. So I think, okay, so I need another pair there, or close that pair, close that pair, close that pair. So lots of parentheses there. But this is what we end up getting if we start, say, okay, well, let's take one of our pairs, right, and use some, algebra. These are standard algebraic properties. And then we have the wonderful Euler's that allows us to express it like this. And then we'd say, well, what happens if I do it with the x to the alpha minus beta I? So similarly, now again, the idea is if I change that plus to a minus, see how it changes. What changes is basically now I'd have a minus here, and I would keep the minus here. So I'm going to skip all of these steps and go right down to this expression where we apply Euler's. So x to the alpha minus beta I, that is equal to x to the alpha and then the quantity cosine of beta ln of x, negative beta ln of x plus I sine of negative beta ln of x, like that. All right, so that's what we have. But again, remember, sine and cosine are even and odd functions respectively. So because cosine is even, this negative here can be ignored, right? It has no effect on the value of the cosine function. So that simplifies to cosine of beta natural log of x. And then because sine is an odd function, that negative can be factored out and makes that plus sign a minus, and then we're left with I sine of beta ln of x, right? So that would be essentially the other function. But the thing is, when we apply our superposition principle, and if I take any constant times this plus any constant times this, if you notice, we have a couple duplicates, right? Because we actually have x times x to the alpha times the cosine of beta natural log of x, and then we have x to the alpha sine of beta natural log of x in both terms. So we basically have this and this, right, as one function, and then we have this and this as the other function. So even if we superimpose these two, we can identify, so we're going to claim that y1 equals x to the alpha cosine of beta natural log of x, right? And y2 equals x to the alpha sine of beta natural log of x, are linearly independent functions and therefore form a fundamental set. So we're going to claim that this function and this function form a basis or fundamental set for the solution of this DE or this case, right? So how do we verify this? Well, we could do the Wronskian, but I want you to take a look to see just how messy it would be, sort of differentiating and setting up our determinant. Remember, an alternative way of establishing the linear independence of two functions is to show that the ratio of the two functions is never a constant, right? So to show that this is not a scalar multiple of this, right? So if we check y1 divided by y2, right? So if this were to reduce to a single constant, right, for all values of x, right, then yeah, I couldn't justify that they're a basis. But if this quotient is not the same, right, then, or I'm sorry, not that the quotient is not the same. I apologize. If the quotient doesn't reduce to a constant, then y1 and y2 must be linearly independent, right? So if we take our x to the alpha cosine of beta natural log of x divided by x to the alpha sine of beta natural log of x. Now remember, again, since x is always positive, then I can reduce the x to the alpha, so that this factor reduces, and then I have cosine over sine, but cosine over sine is cotangent. So this boils down to cotangent of beta natural log of x, right? Which is definitely not a constant, right? And again, for x greater than 0, right, this is not a constant because we have our variable x here. So this is not a constant. And therefore, so what we can say is y1 is not a constant multiple of y2 for all x greater than 0. Therefore, y1 and y2 are linearly independent. So I wanted to remind you of this, right? We've used the Wronskian a bit of late, right? But remember, when you're working with just two functions that you know are solutions to the differential equation, right? That's essentially what we established by using Euler's and all the algebra. We established these two functions satisfy the differential equation. Then we just have to verify that they are linearly independent, and hence we've essentially proven this theorem. So it's like I've given you the proof before the theorem. So here's what it says. So if the roots of a m times m minus 1 plus b m plus c equals 0 are, those roots are this conjugate pair, the alpha plus or minus beta I, then a basis for the solution set of the DE or Cauchy Euler differential equation is, so here are the two functions. So it's x to the alpha cosine of beta log x, and then x to the alpha sine of beta log x, right? And the general solution. So then we can write down the general solution. So in the general solution, again using our superposition principle, is Now you could do the same thing because both functions have a factor of x to the alpha. You can factor out the x to the alpha and then have the c1 times the cosine of beta log x plus c2 times the sine of beta log x. There we go. All right. So let's take let's look at an example of this. So let's see what happens. So let's solve, and let's say it is 4x squared y double prime plus 17y is equal to 0. And let's make it let's go ahead and make it an initial value problem, right? So we'll have y of 1 is equal to -1. Actually, you know what? Let's make it a boundary value problem. Let's take it, let's say the y of e, let's say, is 0. All right. So this is a BVP. We haven't solved one of those in a while, but let's say we have this BVP. So this one has a lot of good things that you have to look out for. For instance, one of the really obvious ones here is the fact that we're missing the y prime term, right? And remember, some of those coefficients could be 0. So if you're missing a term, it's fine. It's still Cauchy Euler, right? We see the power of x there is 2, which matches the order of the derivative there, that's 2. And technically the power of x here is 0 and matches the 0 derivative there, right? So let's write down our auxiliary equation. So it's 4m times the quantity m minus 1. Then I would essentially have plus 0m, which I'm not going to write, and then plus 17, and then that's equal to 0. So if we put this in our standard form, we simply get 4m squared minus 4m, and then plus 17, and then that's equal to 0. Now, if we were to check the discriminant for this, so let's check our discriminant here. So our b squared minus 4ac, that's going to be 16. That's b squared, and then minus 4 times 4, and then times 17. So you definitely see that you're going to get something negative. In fact, it works out to be, what, negative 256, right? So we know that we're in our case 3. So let's see what the actual complex number is, right? Or the pair is. So we have negative b, so that's 4 plus or minus. We know what goes under the square root. That's our negative 256. And then divided by 2a, so that's 8. And let's keep going. So we have 4 plus or minus. This here, the square root of negative 256 is 16i, right? And then this is all over 8. And remember, in order to identify the alpha and beta, we want to make sure that we write this as 2 separate fractions and reduce carefully. So we have 4 over 8 plus or minus 16 over 8i. So the conjugate, the complex conjugate pair is 1/2 plus or minus 2i. So our alpha is 1/2, beta is 2. All right. So once we have this, yeah, we can write down. In fact, let's go through the steps. Here's our basis. So our basis is x to the 1/2 cosine of 2 log x, and then x to the 1/2 sine of 2 log x, right? And just like in the constant coefficient case, again, in your basis, your cosine and sine, they occur as pairs. Just like how you have a pair of complex numbers, conjugate numbers here, your cosine and sine functions show up as pairs in your basis set. Here's our general solution. So let's look at the general solution. What do we have? So it's y equals, and then we could, again, you could write it in this way. You could simply say c1 x to the 1/2 cosine of 2 log x plus c2 x to the 1/2 sine of 2 log x. Or if it's a situation where you see, well, I'm going to have to differentiate. Now, differentiating these will get messy for several reasons. You have the product there, and then you have the chain there because you have a cosine of 2 log x. So, differentiating these wouldn't be trivial by any means. But either way, you can write it in this factored form, right? So you have that, and then your c2 sine of 2 log x, right? Here we go. So let's see our conditions now. So so just as a reminder, the first condition is that y of 1 is -1. So this implies that when x is equal to 1, y is equal to -1. Well, let's see what happens. So we plug -1 for y. Now, when we plug 1 into it, the ln function, right, we are going to get 0, right? So the cosine of 0 is 1, right? 1 to the 1/2 is 1, but then the sine of 0 is 0. So all we're left here is that c1 is equal to 1, right? So we have that one. The other condition says, and remember, this is a boundary condition now because the value of the independent variable is different. This one says that y of e is equal to 0. So that implies that when x is equal to e, y is equal to 0. So I'm going to have a 0 there. Now I have e to the 1/2. Well, e to the 1/2 is the square root of e. I know that c1 is -1, so I'll put that there. So I'll have the negative of the cosine of... Now, the natural log of e is 1. That means I'm going to be left with a 2 as the, inside the cosine function, and then plus c2. Similarly, we'll have the sine of 2 there, right? So we should be able to isolate this, right, and solve for c2. We're just not going to get nice integers, right? That's what's going to happen when you suddenly have these natural logs and things like this showing up in your basis functions. So let's distribute the square root of e. So I'll have 0 is equal to -root e cosine of 2 plus, I'll write it like this, c2 times root e sine of 2. I remember we're solving for c2, so add root e cosine of 2 to both sides. So I'll have, so this be root e cosine of 2 plus is equal to c2 times root e and the sine of 2, and then divide both sides by root e sine of 2. Well, that works out nicely because the root e goes away, but I have the cosine of 2 divided by the sine of 2, which I am just going to write as the cotangent of 2. So that's the constant c2. So here is our particular solution, right? So our particular solution, I'm just going to write it in this with the factored form. So y is equal to x to the 1/2, and then we'll have negative cosine of 2 natural log of x, and then plus the cotangent of 2 times the sine of 2 times the natural log of x. So you never know. And again, remember, with the boundary value problems, we're not necessarily guaranteed a solution, or a unique solution for that matter. But in this case, it worked out nicely. Just that one of our coefficients ended up being a transcendental number, right? But those are fun too. So there you go. So now we've been able to handle all three cases associated with the Cauchy-Euler equations, and we will just keep chugging along. See you soon.